So next I am going to start this topic collisions, which is after center of mass and conservation of linear momentum. In some of the books, collisions is also given in the same under the same headings, conservation of linear momentum. But in some of the standard books, it has been dealt separately. So here I am going to deal collision separately. Of course, it can also be treated as a continuation of conservation of linear momentum. So first I am going to discuss the theory part for collisions. So don't write the running notes when I am explaining the theory part. You concentrate only to listen to my discussion. So after discussing some theory part, I will be showing you the notes or PowerPoint presentation that, for you. Then you can write the notes. So I will be telling you when you can write the notes in case you are writing the notes here. So at present you just concentrate only to listen. Don't start writing the notes. Don't write running the notes when I am discussing. So as I discussed in the previous chapter, conservation of linear momentum, center of mass and conservation of linear momentum. So whatever may be the system you choose, you may choose 2 particles as one system or 3 particles as one system. A number of particles can be considered as one system. A rigid body can also be considered a system of particles of which it is composed of. So when you consider 2 or more number of particles or objects as one system, then the force applied or exerted by one particle in the system by another particle in the same system is called as the internal force. The force exerted by one particle in the system on another particle in the same system is called as internal force. And the internal forces cannot change the total linear momentum system. The total linear momentum of system changes only due to the external forces acting on the system. So if you consider the case of collision of 2 bodies with masses m1 and m2. First we consider the general case, later we will specifically discuss about one-dimensional collisions. Let us consider the 2 bodies with masses m1 and m2, which have velocities u1 bar and u2 bar just before they collide with each other. So at the time of collision, m1 exerts a force on m2, which is denoted by F bar subscript 2(1). That is the contact force on m2 by m1 or interaction force on m2 by m1, which is denoted by F bar subscript 2(1). The force of interaction, the reaction to this force, that is the force on m1 by m2. Denoted by F bar subscript 1(2). That means the first number in the subscript represents the particle on which the force acts. The next number in the subscript represents the other particle which applies that force. So let us suppose the time of collision is very short. The time of collision is usually denoted by delta t, is very short, mathematically speaking tending to 0. It may be for infinitely small time interval, we can denote it by dt. So let us consider a simpler situation where no external forces act on the system of the 2 mass m1 m2. I mean, let us suppose the net external force acting on the system of the 2 mass m1 and m2 is 0. for a finite time interval before and after the collision and during the collision also. That means only unbalanced force on M1 during the time of collision is F bar 1, 2. And only unbalanced force acting on M2 during the time of collision is F bar 2, 1. That means we are considering a simple situation where no external forces act on system of the two mass M1, M2 during the time of collision delta T. Then from Newton's third law, you can write F bar 1, action equal negative of reaction. From Newton's third law, we can write action and reaction are equal in magnitude but opposite in direction. So mathematically, you can write F bar 1, 2 equal negative F bar 2, 1. For infinitesimally small interval of time, the impulse given to the mass M1, F bar 1, 2 is the force on M1 by M2. So F bar 1, 2 dt gives you the impulse given to the mass M1 during the infinitesimally small interval of time dt. That can be the minus of F bar 2, 1 into dt, which is the impulse given to the mass M2 during the same time interval dt. The impulse gives you the change in the linear momentum. The impulse of the resultant external force on a particle gives you the change in momentum of the particle. That means F bar 1, 2 dt, if you integrate both sides for the time of collision, that means if you consider for the time of collision, this gives the change in linear momentum of M1 in the time interval delta t, which you can write M1 V1 bar minus M1 U1 bar. Here U1 bar is initial velocity of M1 just before collision. Some of the books it may be denoted by V1I, and some books U2 may be denoted by V2I. U2 bar is the velocity of M2 just before collision, which may be also written as V2I, V subscript to I, that is initial velocity of M2. So M1 into V1 bar minus U1 bar, that is final momentum of M1 just after collision minus initial momentum of M1 just before collision. Remember, the difference which we are writing on the left side is a vector difference. Is equal to negative of change in momentum of M1. So we can mathematically write delta P bar for M1, negative of delta P bar for M2. Delta P bar means change in the linear momentum of mass M1. Delta P bar subscript 1 means change in linear momentum of mass M1 during the time of collision. Delta P bar subscript 2 means change in linear moment of second mass M2 during the time of collision. So this you can delta P bar subscript 2 is change in linear moment of second mass M2. You can write M2 into V2 bar minus U2 bar. V2 bar is the velocity of M2 just after collision. V1 bar is velocity of M1 just after collision. In some of the books, textbooks, that is V1 bar may be written as V bar subscript 1F. And V2 bar may be written as V bar subscript 2F. V bar subscript 1F represents the final velocity of M1 just after collision. V bar subscript 2F represent the final velocity of M2 just after collision. But I follow this notation, which is simpler to write for the students. You can follow any one of the notations. So you can collect the terms containing U1 bar, initial velocities to one side of the equation, final velocity to the left side. So this you can write it as M1 V1 bar plus M2 V2 bar equal to M1 u1 bar plus m2 u2 bar. So m1 u1 bar is the initial momentum of m1 just before collision. So m2 u2 bar is the initial momentum of m2 just before collision. So vector sum of the linear momenta of the two mass m1 and m2 just before collision. That is what you have on the right side of the equation. m1 v1 bar is the linear momentum of the first mass m1 just after collision. m2 v2 bar is the linear momentum of the second mass m2 just after collision. So m1 v1 bar plus m2 v2 bar, the vector sum of the linear momenta of the two masses just after collision. So vector sum of the linear momentum of the two masses just after collision will be equal to the vector sum of the linear momentum of the two masses just before the collision. In the problems we deal in collisions, there are two types of situations. The first simpler situation is the problems where no net external force acts on system of the two masses m1 and m2 during the time of collision. Then total moment of system of the two masses at a later instant after collision can be taken as equal to total linear moment of system of the two masses at an earlier instant before the collision if no net external force acts on the system of the two masses between the two instants. But some of the problems, the net external force on system may not be zero. But if the time of collision delta t is very small, tending to 0, we can write vector sum of linear momentum of the two masses just after collision can be equated to the vector sum of the linear momentum of the two masses just before collision, assuming that change in the linear momentum system of the two masses during the time of collision due to the external forces is negligible when the time of collision is very short. So in all the examples we deal in collisions, it is understood unless, even if it is not specified, unless you have specifically mentioned, the time of collision to very small. So that vector sum of the linear momentum of the two masses just after collision can be equated to the vector sum of the linear momentum of the two masses just before collision. So the collision between two masses may be one-dimensional or two-dimensional or three-dimensional. Of course, we first discuss about one-dimensional collisions. Next time we'll be also discussing about two-dimensional collisions. So in the case of two-dimensional collisions, if the two bodies, that means if the two velocities before collision and velocities just after collision, if they are confined to single plane, then it can be called as two-dimensional collision. In the two-dimensional collision, suppose if the plane in which the two masses move before and after collision, we can consider it as xy plane. The velocity v bar of a body moving in the xy plane can be written in the form I cap into Vx plus j cap into Vy. But first I am going to discuss the one-dimensional collision to start with. Later specifically I discuss two-dimensional collisions. So in the one-dimensional collisions, I mean collision is said to be one-dimensional. Velocity is just before collision and velocity is just after collision. If they are direct along same straight line, then the collision is called one-dimensional collision. One-dimensional collision is sometimes also called as head-on collision. So if the initial velocities u1 bar and u2 bar just before collision, and the velocities v1 bar and v2 bar just after the collision, if they are direct along same straight line, then it can be called as one-dimensional collision or head-on collision. The velocities are direct along same straight line does not mean same direction. So in a one-dimensional collision, the two velocities before collision may be either in the same direction, or some cases they may be in opposite directions, or in some cases one velocity may be 0 before collision. One body may be at rest, another body may be in motion. So for one-dimensional collision, it's not compulsory to follow this bar, strictly to follow this bar notation. Of course, it will not be wrong even if you follow the vector notation or bar notation even for problems of one-dimensional collisions. But for convenience, for simplicity, we can express the velocity scalar notation. Suppose we'll consider the simplest situation where all the velocities are direct along x-axis. If all the velocities are direct along x-axis, then u1 bar you can write u1 into I cap. u2 bar you can write u2 into I cap. u1 and u2 are the x components of initial velocities before collision. v1 bar you can write v1 into I cap. I cap is unit vector along positive x-axis. v2 bar you can write v2 into I cap. So I have I cap in every term on both the sides. So in the case of one-dimensional collision, the equation can be written in more simpler way. m1 v1 plus m2 v2 equal to m1 u1 plus m2 u2. That means, for convenience and simplicity in writing the equation, for problems we are going to discuss in one-dimensional collisions, we try to express the velocities in the scalar notation. That means without using bar symbols. Of course, it will not be wrong even if you follow vector notation. In advance, some of the standard books, they solve all the problems in vector notation, irrespective of whether collision is one-dimensional or two-dimensional. But as per the method followed in the regular board textbooks, for problems in one-dimensional collisions, we can write the equation in simpler form without using the bar notation. We have to simply give positive sign for velocities in one direction and give negative sign for velocities in the opposite direction. In case you are already given the velocity, numerical values of the velocities and directions of velocities are mentioned. But we don't put negative sign for the unknown quantity when you do not know in a velocity after the collision. So after calculation, we automatically will come to know the direction and magnitude of velocity. So in the problems in one-dimensional collisions, we give positive sign for velocities and linear momenta in one direction, and simply give negative sign for velocities in the opposite direction. I mean, if numerical are given, then you can write the equation scalar form. So that will be convenient for simplification. So now I am going to confine my discussion about one-dimensional collisions. Don't write the running notes when I am explaining or discussing. Don't write running notes when I am explaining or discussing here. You can write the notes later. I will show you the notes later separately, the typed form. So in the case of one-dimensional collisions, we write m1 v1 plus m2 v2 equal to m1 u1 plus m2 u2. In some of the books, the same equation can be written in different notation. m1 v1f plus m2 v2f equal to m1 v1i plus m2 v2i. So I try to follow this notation on the left side. But in case you are already accustomed to follow the notation on the right side, you can follow the same notation on the right side. Nothing wrong. Here we mean u1 or v2i means initial velocity before collision. u2 or u1 or v1i means initial velocity of m1 just before collision. u2 or v2i is the initial velocity of m2 just before collision. v1 or v1f represent the final velocity of m1 just after collision. v2 or v2f represent the final velocity of m2 just after collision. So this equation I number it as 1. This equation 1 holds good for all one-dimensional collisions, irrespective of whether the collision is elastic one-dimensional collision or inelastic one-dimensional collision. So a collision is said to be an elastic collision. The total kinetic energy of the two colliding masses just after collision same as the total kinetic energy of the two colliding masses just before collision. That means if the two colliding masses have surfaces which are perfectly elastic in nature, then during the time of collision, there will be elastic deformation of the two colliding bodies. That means there will be temporary change, elastic deformation in the dimensions of the body, or we call elastic deformation within the elastic limit. But if these deformations are within the elastic limit, that means a part of the initial kinetic energy before collision may get converted into elastic potential energy during the time of collision in the case of elastic collision. But after the two colliding bodies get separated from each other, then no impulsive forces act. The impulsive forces between the two masses M1 and M2, which I have denoted by F bar 12 and F bar 21. This F bar 21 and F bar 12, they denote the internal forces or forces of interaction between the two colliding masses, which act only for a very short time interval during the time of collision, which we call impulsive forces. Due to these impulsive forces, each colliding mass may undergo a temporary deformation, elastic deformation within the elastic limit, so that a part of initial kinetic system of the two colliding masses may get converted to elastic potential energy of deformation during the time of collision. But after the collision is over, I mean the two colliding masses get separated, the two masses completely regain back their shape and dimensions if the collision is perfectly elastic. That means elastic deformation potential energy gets converted back to kinetic energy. So that some of the kinetic energies of two colliding masses just after collision can be equal to some of the kinetic energies of the two colliding masses just before collision. But don't mistake the total kinetic energy of two colliding body masses remains constant during the time of collision. Total kinetic of two colliding masses during the time of collision should not be mistaken to be same as total kinetic energy before collision. The correct statement is that in the case of elastic collision, the total kinetic energy of two colliding masses just after collision, same as the total kinetic energy of two colliding masses just before collision. So in the case of an elastic collision, we can write some of the final kinetic energies of the two colliding masses just after collision is equal to some of the initial kinetic energies of the two colliding masses just before the collision. So this equation 2 holds good only for elastic collisions. That means equation 2 holds good for one-dimensional elastic collisions. Equation 2 also holds good for two-dimensional elastic collisions. Equation holds good. First equation 1 holds good only for one-dimensional collisions. That means equation 1 is applicable both for one-dimensional elastic collisions, and equation 1 is also true for one-dimensional inelastic collisions. So now for this class and also probably the next class also, we'll confine our discussion for one-dimensional elastic collisions. Later I discuss about one-dimensional inelastic collisions separately. Collision is said to be inelastic or non-elastic if the total kinetic energy of the two colliding masses just after collision not equal to the total kinetic of the two colliding masses just before the collision. So in the case of one-dimensional elastic collision, both the equations 1 and 2 will be applicable. So next I am going to discuss or derive the relationship between the velocities v1 and v2 and u1 and u2 in the case of one-dimensional elastic collision. So in each equation I carry the terms containing mass m1 to one side and mass m2 to the right side. So in the first equation, if you collect the terms containing m1 to the one side, m1 into v1 minus u1 is equal to, on the right side you can write m2 into u2 minus v2. From second equation, we'll take the terms containing m1 to the left side here. In the second equation also, half m1 into v1 square minus u1 square is equal to half m2 into u2 square minus v2 square. Now I am going to eliminate the mass m1, m2. I divide this equation with this equation. So therefore we get this 1 by 2 you can cancel on both sides. On the left side you can write m1 into v1 square minus u1 square. You can write v1 minus u1 into v1 plus u1 divided by earlier equation m1 into v1 minus u1. The right side here in the second equation, m2 into u2 square minus v2 square can be written as u2 minus v2 into u2 plus v2 divided by this equation m2 into u2 minus v2. So on the left side mass m1 gets cancelled, right side m2 gets cancelled. Here v1 minus u1 gets cancelled. Here u2 minus v2 get cancelled. So on the right side, left side you get v1 plus u1 is equal to v2 plus u2. So you get v1 plus u1 equal to v2 plus u2. That is sum of the final and initial velocities of m1 is equal to sum of the final and initial velocities of m2. If you take the final velocities one side of the equation, initial velocity to the other side of the equation, from the same equation you can write u1 minus u2 equal to v2 minus v1. So u1 minus u2 gives you the relative velocity of m1 with respect to m2 before collision. v2 minus v1 you can write negative of v1 minus v2, or same equation you can write v2 minus v1 is equal to negative of u2 minus u1. v2 minus v1 the relative velocity of m2 with respect to m1 just after collision. u2 minus u1 is the relative velocity of m2 with respect to m1 just before collision. You can observe that v2 minus v1 is negative of u2 minus u1. That means the relative velocity of m2 with respect to m1 just after collision is a negative of relative velocity of m2 with respect to m1 just before collision. So if you consider the magnitudes only, you can say that magnitude of relative velocity between the two colliding masses just after collision when they get separated will be same as the magnitude of relative velocity between the two colliding masses just before collision. Of course, this is true only in the case of one-dimensional elastic collision. So the present discussion is about one-dimensional elastic collisions. That means in the case of one-dimensional elastic collision, the magnitude of relative velocity between the two colliding masses just after collision same as the magnitude of relative velocity between the two colliding masses just before collision. So I am going to now show you the notes for what I have already discussed. That means I would like to summarize the whole discussion I have done so far in this class. Now those who are writing the notes, now you can get ready with your notebook and pen. So now I am going to show you the notes for what I have so far discussed in collisions. So come on, look at the screen here now. So I'm going to show you the notes for collisions, summarize the discussion I have done. Look at the screen. I will read out the notes. So those who want to write the notes, they can start writing the notes. In case you need more time to copy the notes at any time, more time than given here, you can take a pause and take your own time, because all the students may not need same interval of time to copy the same notes. Come on, look at the screen. If two masses m1, m2 moving with velocities u1 bar, u2 bar, respectively, collide with each other, such that the time of collision is extremely short, within brackets I have written delta t tending to 0, then we can write m1 v1 bar plus m2 v2 bar equal to m1 u1 bar plus m2 u2 bar in vector form. So this equation is a more general equation which we write for all examples in collisions. Either the collision is one-dimensional or two-dimensional. Of course, the collision may be three-dimensional also, but we are not going to deal examples of three-dimensional collisions at present for the students at the 11th class or intermediate level, where v1 bar and v2 bar are the velocities of m1, m2 respectively just after collision. For a one-dimensional collision, we can write m1 v1 plus m2 v2 equal to m1 u1 plus m2 u2. This we call equation number 1. Come on, copy down this. In case you need more time to copy the notes, you can take a pause and copy the notes. In case you need more time to copy this, you can take a pause and take your own time to copy the notes. Next, I am going to show you the continuation for this. Equation 1 is applicable both for elastic and inelastic one-dimensional collisions. So equation 1 is applicable both for elastic and inelastic one-dimensional collisions. For a perfectly elastic collision, can write half m1 v1 square plus half m2 v2 square equal to half m1 u1 square plus half m2 u2 square. So if you solve the equations 1 and 2 as explained before, for a one-dimensional or head-on elastic collision, you can write v2 minus v1 equal to u1 minus u2, which you call equation number 3, or v2 minus v1 equal to negative of u2 minus u1. So any problem in one-dimensional elastic collisions can be solved by using the equations 1 and 3. So come on, copy down the notes. In case you need more time to copy the notes, you can take a pause and take your own time. So you can see the diagrams. I have shown the diagram for simpler situation, one-dimensional collisions. U1, U2 represent the initial losses of M1 and M2 between two collisions when we consider case one-dimensional collision between two elastic spheres moving in the horizontal direction. V1 and V2 denote the velocities of M1 and M2 just after collision. As I written in the earlier equation, you can see V2 minus V1 in the equation 3 equal to U1 minus U2. Suppose if U1 is greater than U2, then the difference U1 minus U2 is positive. The right hand side of the equation is positive. The left hand side of the equation must also be positive. So if U1 minus U2 is positive, V2 minus V1 is positive. That means V1 will be less than V2 when U1 is greater than U2. So if U1 is greater than U2 before collision, then after collision V1 will be less than V2. Means before collision, if M1 is moving, I mean before one-dimensional elastic collision, I mean if M1 is moving faster than M2 in this figure before collision, then after collision M1 will be moving slower than M2. That means in a one-dimensional elastic collision, after the collision, the faster body gets slowed down and the slower body will be speeded up. That means suppose if M1 is moving faster than M2 before collision, then after collision M1 will be moving slower than M2. I mean in the case of elastic one-dimensional collision. The whole discussion is about elastic one-dimensional collision. So in a one-dimensional elastic collision, the magnitude of the relative velocity of separation just after collision will be equal to the magnitude of the relative velocity of approach just before the collision. Come on, copy down this. Up to here. Those who are writing the notes, please copy down the notes up to here. In case you need more time to copy the notes, you can take a pause and take your own time to copy the notes. Next, I am going to continue this discussion for one-dimensional elastic collisions. That means I am going to derive the expressions for V1, V2 in terms of U1, U2 and masses of the two colliding bodies in the case of one-dimensional elastic collisions. So, after copying up to here, please stop writing. Again, you concentrate only to listen. You can now stop writing after copying this. So, in the case of one-dimensional elastic collision, we can solve any problem by using the equations which I have written earlier. M1 V1 plus M2 V2 equal to M1 U1 plus M2 U2. This is one equation. And another equation is V2 minus V1 equal to U1 minus U2. So any problem in one-dimensional elastic collision can be solved by making use of these two equations. That's all. Almost all the problems in one-dimensional elastic collisions can be solved by using these two equations only. But I am going to derive the direct expression for V1, V2 in terms of U1, U2, so that in case you are able to remember those direct expressions for V1, V2, you can may be able to solve the problem still more faster in objective type examination. So to derive the expression for V1, we have to eliminate V2 from these two equations. From this equation, V2 minus V1 equal to U1 minus U2. Can write V2 equal to V1 plus U1 minus U2. We'll substitute this value of V2 in the equation number 1. Substituting this value of V2 in the equation number 1, can write M1 V1 plus M2 into V2. We can write V1 plus U1 minus U2 equal to M1 U1 plus M2 U2. Now we can solve for V1. That means collect the terms containing V1 separately and terms containing any velocity U1 and U2 to the right side. So you get M1 V1 plus M2 V1 plus M2 U1 minus M2 U2 equal to M1 U1 plus M2 U2. You can solve for V1. You can take V1 common in the first two terms on the left hand side, and these two terms will transfer to the right side. So here if you carry this term to the right side, M1 U1 plus M2 U2 minus M2 U1 plus M2 U2. Take U1 common in these two terms. So M1 minus M2 into U1 plus adding these two terms, M2 U2 plus M2 U2, can write 2m2u2. That is equal to v1 into m1 plus m2. So velocity of m1 just after collision will be equal to m1 minus m2 by m1 plus m2 into u1 plus 2m2 by m1 plus m2 into u2. Similarly, you can solve for v2 also by eliminating v1 from the two equations. From this equation, you can substitute this value of v1 in this equation to find v2. That is one method. Other method is you can eliminate v1 from these two equations. You can find v2. From this equation, you can write v1 equal to v2 plus u2 minus u1. And this value of v1 you can substitute in this equation, first equation. That is m1 v1. v1 you can write again v2 plus u2 minus u1 plus m2 v2 equal to m1 u1 plus m2 u2. You can solve this equation for v2. If you solve this equation for v2, you get v2 equal to 2m1 by m1 plus m2 into u1 plus m2 minus m1 by m1 plus m2 into u2. The simplification, you can easily do it for the last one. So finally, in the case of one-dimensional elastic collision, the final velocity of m1 just after collision is given by m1 minus m2 by m1 plus m2 into u1 plus 2m2 by m1 plus m2 into u2, and v2 can be written as 2m1 by m1 plus m2 into u1 plus m2 minus m1 by m1 plus m2 into u2. So next I am going to show you the notes for the same discussion. So those who are writing the notes, and then they can again get ready with your notebook and pen to copy the continuation. I mean notes for continuation of the earlier part of the notes. So the expression for final velocity just after collision in the case of one-dimensional elastic collision are v1 equal to m1 minus m2 by m1 plus m2 into u1 plus 2m2 by m1 plus m2 into u2, and v2 equal to 2m1 by m1 plus m2 into u1 plus m2 minus m1 by m1 plus m2 into u2. You can copy down this. In case you need more time to copy this, you can take a pause and copy this. So next I am going to discuss the special cases in one-dimensional elastic collisions. So better I discuss about the special cases in one-dimensional elastic collisions in the next class. So in the next class, I am going to discuss some special cases in one-dimensional elastic collisions. And some of these special cases are discussed even in the board textbooks. A number of questions were given in the past entrance exam papers based on these special cases. Then after that, I will be discussing some problems on one-dimensional elastic collision. After that, I will be discussing one-dimensional inelastic collisions in the next classes.